Got a couple of questions. Okay, Bernoullis equation, 1/2 rho v squared plus rho gy plus p doesn't change within a continuous fluid. Okay? Where rho is the density at a point, v is the speed of the fluid at that point, p is the pressure at the same point, y is the altitude at the point, and g is just the acceleration of gravity, which for our purposes and for almost any purposes can be regarded as completely constant. So it doesn't vary. Okay? Now for an incompressible fluid, which one of these quantities isn't going to vary?
Incompressible? Pressure?
No, pressure can vary. I can take that bottle, seal it off, and squeeze it, and I'll change the pressure.
Density?
Density isn't going to change. Okay? Which makes things a lot simpler than if it did, which it does for air, which is why we're doing incompressible fluids right now. Talk a little bit about what happens with air, but the math gets pretty challenging. You really got to have calculus to do that, and actually quite a bit more than that. Okay, to completely analyze what goes on, actually get into the Navier-Stokes equations, which involve tensors and all kinds of stuff that you won't know anything about for some time. Okay. Okay, so I'm going to ask a simple question. Let's say between here and here we have a continuous incompressible fluid, like water here and water here. Now the water might be in a big container. There might be a big container around these 2 points, right? Or there might be tubes between here and here that change diameters. Okay? But let's just say that we know that between here and here, speed doesn't change. Okay? What does change between here and here?
Altitude.
I'm sorry, altitude, right?
Yeah.
This is higher than this. Now, I have been specific about altitude, but altitude is measured along the line in which gravity works, along the line of gravity, basically. Okay? In our case, pretty much just directly away from the center of the Earth. Okay? So anyhow, okay. Now, altitude is greater here than it is here, right?
Mm-hmm.
So what does this equation say? Okay, if the speed doesn't change, then this thing doesn't change, does it? It's incompressible, right? So this one is out of it, and now the sum of these two things can't change. Okay? Since the speed can't change, and the sum of these three things can't change, then the sum of these two things has to stay the same, right? Okay? This doesn't change, and the whole thing doesn't change, so some of these two don't change. Meaning that altitude is less here than it is here. What's that say about pressure?
It's gotta be less of the.
How does the pressure between here and here change? Altitude's greater here than it, say this is point A and this is point B, right?
Mm-hmm.
Altitude at A is greater than altitude at B.
Yeah.
What can you say about the pressure?
Pressure's lower at the top.
Yeah.
Where's the pressure greater?
At the bottom.
Yeah. Yeah. Because from A to B, this is decreasing, right? I mean, rho's positive, acceleration of gravity is a positive constant, right? So if y is less at B than it is at A, then if you go from A to B, this decreases. But the whole thing has to stay the same, and this isn't changing, so the pressure has to increase. Well, this might be a swimming pool. If you're here versus here, where's the pressure greater?
Over.
Yeah, leave it to the swimmers to answer, okay? But, common experience of water, right? You go deeper, the pressure increases. That comes right out of Bernoullis equation, okay? There are other applications. I mean, let's say now that we have our two tubes, and they're both running horizontally. Okay? Now, if the two tubes are running horizontally, and this is a point in the bigger tube, and this is a point in the smaller tube, what changes between here and here?
The diameter of the tube.
Well, yeah, but you don't see the diameter of the tube in this
No,
equation.
no.
But what doesn't change between here and here?
The altitude.
Altitude.
Yeah.
So now we know this isn't changing, right?
Yeah.
Okay? Now, what happens to velocity, assuming fluid is flowing through these tubes?
It gets faster.
I'm sorry?
It increases. It gets faster.
Velocity from here to here, this being the smaller tube, increases, as we just proved. Okay? Which means, what about the pressure?
Increases.
It increases.
If velocity increases, it has to decrease.
Okay, so at which point is the pressure greater?
Here.
Yeah. Velocity increases, pressure has to decrease. Now, there's a reason for that. Intuitively, you don't have to know a lot of physics. How are you going to speed the water up?
Gotta force it through.
It takes force to speed the water up, right? Where's the force come from?
pressure.
Pressure. So you use up pressure basically to speed the water up. That's not a very accurate statement, but intuitively, and that's the best we're going to do here because we're not really doing the physics. Okay? Pressure decreases in order to speed up the water. Okay? You're doing work, and it gets into work and energy, and I don't want to get into a deep explanation of that. Okay? At least not in class. Okay, so we understand how this could be useful in analyzing fluids, right? Okay, and it's a good thing. I mean, this is really a powerful and important equation, and the algebra of it isn't that bad. So,